Welcome back to part two. Now, what we're going to do in this video is take four examples of separable differential equations. Now, the first two are going to be asking us to find what's called a general solution, and that means that the derivative is given, but that's it, no other information given, so we will be able to find an equation where the integration constant will not be able to be solved for. We'll just have to leave the integration constant in the equation as an unknown constant plus c. In the other two examples, there will be more information given, similar to when you were working with your slope fields. There will be an ordered pair given, and you'll find the particular solution whose graph would pass through that given point. Okay, so the first one I've got is the derivative of y is equal to 2y. Interesting that the derivative of the function y is equal to the function itself times 2. I actually encourage you to just pause for a minute and think. Can you think of an example of a function that we might have worked with this year that would meet this property that the function's derivative is just 2 times what the function originally was? Interesting. Well, we're going to try the separated variable method, and we'll arrive at the answer in a second here. Remember, so the step one is to change all derivative notations to dy over dx. So that'll just be what I do first. And then the next goal is to get all the y's and dy's on the same side. That means right now we're going to separate the dy from the dx by multiplying by dx. Okay, so dx will come over to the right side. And now I need to get the y over to this side. Now it's pretty tempting just to go ahead and divide by 2y, and you could do that. So many people would maybe think to divide by 2y here and just leave dx. Okay, now you can work with that. However, I think the next step where it's going to be integrated, I think actually it's going to end up being a lot easier if you had left the 2 over on the right. Okay, it works either way, but I think I would like to leave it there. So I'm not going to divide by 2y, I'm only going to divide by the y. Okay, so that brings y over to there. So now my separated equation is dy over y equals 2 dx. I'd like to encourage you to pause the video at this stage because the next step is integration. Okay, and what I'm going to do is I'm going to put my integration symbols there. And I encourage you just to pause for even maybe 30 seconds and examine the two integrals and see if you know how to integrate each side. Okay, well, hopefully you've tried to look at each of those integrals. Now on the right side, we're integrating only a constant, so integral of 2 is 2x. And on the right, I'm hoping you recognize dy over y. Really, it's the same as dx over x, or maybe the more general du over u. This is a natural logarithm integral. So the antiderivative is the natural log of the absolute value of y. Now remember, in the first example in the other video, we put a plus c1 for the integration constant on this side and then a plus c2 on this side. But the next step would always be to combine the constants into a single constant. So from now on, I'm just going to put plus c always on the x side. Okay, so we're just going to put plus c there and then call that good. Now, you could leave this right here and call that your general solution because now all the differentials have been removed, right? This is just a standard equation involving x and y and a constant. However, it's always a good idea to try and solve for the function. So what I'm going to now try and do is solve for y, right? So starting back up at the top, the natural log of y equals 2x plus c. Now going back to your pre-calc days, if you have an equation with a log around the variable you're solving for and you're trying to solve for that variable, a common way to do this is to exponentiate each side. So we're actually going to be raising each side and making each side the power of the base e. Okay. Now e to the power of the log of y. That makes those inverse operations. And so we end up with y. Okay? On this side, this is where you got to be careful because 2x plus c is all entirely the power of e. In fact, think back to when you add, when do you add exponents? Well, again, go back to your pre-calc or algebra days. You add exponents when you're multiplying with a common base. So we could actually separate this into e to the 2x times e to the c. And see, that's where the common base requires that you add the exponents. We really just use that property in reverse there. The reason I did that is because now I've separated e to the 2x, which is the part involving the variable, and then over here, this is all still now just a constant. Now, for this time, I'm going to rename this whole thing e to the power of this constant. Let's just let that equal let's pick another letter like capital A now, and let that be another constant that came from e to the c. And so my final form is a, constant a, times e to the 2x. Okay, now, just like when you solve equations in algebra class or what have you, you can always check your differential equation to see if it in fact satisfies the differential equation that you were starting with. So let's actually do that here. Remember that if I take the answer that I now have and work out its derivative, it should follow the pattern that's up there. So the derivative of y, the equation I'm working with, would be a times e to the 2x. But remember, this requires the chain rule. You would have to multiply by 2. And now look at this. If I parenthesize a times e to the 2x, that was your original function y, wasn't it? And so we really do have y prime equals 2y, which is what we were asked to solve. So verifying that this equation actually is a solution of this differential equation there. Okay, let's look at another example of this. I've got y prime times x equals x squared, or sorry, square root x, y squared. And this time, you're going to be finding the particular solution that passes through the point 0, 5. So in other words, you'll be working past just generally solution involving plus a constant, and you'll be finding the plus c. Okay, so let's start by dy dx times x equals the square root of x times y squared. Now this time what I encourage you to do is pause the video right here. You've seen me separate variables a couple of times. I encourage you to try and just pause the video for a minute and see if you can do algebra far enough to get the variables separated. And then we'll check back with you in just a minute. Okay, hopefully you've had a chance to try separating the variables. Now I'm going to start again by separating the dy and dx by multiplying dx. Think of it as multiplying dx to the other side. So I've got x times dy equals square root x times y squared dx. Now, so I'm now going to bring this other x over to the other side as well by dividing. And in the same step, I'm going to move the y squared over to the left by dividing by y squared. So my left side is now y dy, dy over y squared. And this is root x dx over x. So the variables are separated. However, I would question whether this is the best way to leave it. When the next step is going to be integration, we want to look and see if I just put the integration symbol on these, would we know what to do with either of the two sides? Common mistake is to look at this and it looks a lot like the last one, that was dy over y, and it ended up being a logarithm. Remember that this is not a logarithm if it's not dy over y. This is dy over y squared. I really think this is one good way to rewrite that left side is to rewrite it y to the minus 2 dy here, because then you can just use the power rule to integrate this. And really, this needs to be combined as well. So let's think of root x as x to the 1/2. Okay, I'm just going to write it there to remind us. X to the 1/2 divided by x to the first. And let's combine that by subtracting the exponents. It would be x to the minus 1/2 dx. Okay, and then we're going to be integrating that also by the power rule. Okay, so integral of the left side with the power rule would become y to the minus 1 divided by minus 1, or in this case, you could just multiply by minus 1. Integral of x to the 1/2, the power would bump up to plus 1/2, and then you'd have to multiply by 2. So it'd be x to the 1/2 times 2. And remember, we'll put the integration constant on one of the two sides right there. And let's go ahead and now rewrite this without the negative exponent. So negative 1 over y equals 2 square root x plus c. Now, once you get to here, you can actually take this and use your given condition to solve for the plus c at this stage, or you can wait until later. Let's try it right now in this one. So this says when x equals 0, the y has to be 5, right? So by plugging in 5 for y, it would be negative 1/5 equals 2 square root of 0 plus c. And basically that tells you that in this equation, the c is negative 1/5. Okay, so we've got to go back now and write our equation with that filled in. Negative 1 over y equals 2 root x minus 1/5. Now, I would like the solution to always be, if possible, solved for y. I don't have that right now. I've got it solved for negative 1 over y. So we're going to open up a new screen here, and we're going to continue where we left off right here. So here's where we left off. We had the equation negative 1 over y equals 2 square root x minus 1/5. Our goal is to get y by itself here. One way to do this would be to start with multiply everything by negative 1 to get the negative off of there. So now just 1 over y would equal negative 2 root x plus 1/5. Now, since I have 1 over y, which is just the reciprocal of y, a nice way to do this is just to flip both sides upside down. Now be careful, this is all over 1 right now. So when I reciprocal this side, it's going to become 1 over the whole thing, even the 1/5. Okay, so it's now y equals positive 1 over the quantity negative 2 root x plus 1/5. And since we don't really want the fraction within a fraction, we're going to finish it off by multiplying by 5 over 5. So my final equation is going to be y equals 5 over negative 10 root x plus 1. So that, guys, is your equation solved for y, and the derivative of this equation will satisfy the derivative or the differential equation in the previous screen. Okay, we'll do one more together for you today, and that will be this one right here. I've got the equation x squared plus 4 times dy dx equals x times y, and again we're looking for the particular solution. I'm going to use that same ordered pair, 0, 5 again. And so now this one's already got the notation dy over dx in it. And let's actually start this time, but we're going to multiply by dx to this side. And so that would leave us x squared plus 4 dy equals xy dx. Now, obviously, we need to get this y over to this side, so we'll have to divide it. Okay, so we'll be dividing by y here. Now, I also obviously have to get x squared, the quantity x squared plus 4 over to this side. So now, instead of distributing dy here, because that's going to make it very difficult to separate the parts, what we're going to end up doing is just divide by the whole quantity x squared plus 4. Okay, so we're going to go in like this and bring it over here like this. Okay, let's clean up our little mess here. So dy over y is now x dx over x squared plus 4. So now the variables are separated, and we're going to put our integration sign. And then one more time, I'm going to encourage you here to pause the video and on your own see if you can integrate each side of the equal sign. That's a very important thing. We're going to all of these problems, we review our integration skills for sure. So pause for a minute here, see if you can solve each of these integrals. Okay, hopefully you did that. And either way, we'll do it together now to verify if you did try it. The left side is one we've seen today already. Dy over y is the derivative of the natural log of y. Now, on this side, you want to look carefully here. There's not really a good way to try and combine the numerator with the denominator, so maybe you caught on that this is a good one where we make a u substitution. If we substitute for x squared plus 4, du is 2x dx. So x dx would be 1/2 du, right? So just as a side note, this integral now is 1/2 integral du over u, which makes this another natural log integral, but times 1/2. So I've got 1/2 natural log of u. Now I'm going to go back and remember that u was x squared plus 4. And there we add our plus c. And at this stage, notice I didn't put the absolute values around x squared plus 4 because there's no way that that can ever be negative. And it's also a good idea at this point that this 1/2 multiplying by the log, that 1/2 can become the power of x squared plus 4. So let's go ahead and write this now as the natural log of y equals the natural log of the square root of x squared plus 4, all plus a constant. And just like in the previous example now, the way to get y by itself is to exponentiate each side this way. And then don't forget now, e to the log of y is just y. And on this side, remember, we separated into two parts because of the addition happening in the power. It's times e to the c. And we're going to do that little move again where this entire quantity is still a constant, and we're just going to rename it a. And so y is equal to the constant a times, and here again we have inverse things. We have e to the power of a log, and that makes it back down to just the square root of x squared plus 4. So my first landing spot here is this general solution, y equals a times the square root of x squared plus 4. Now we want to finish it off by noting that we have to have the solution where the point 0.5 is a solution point. So let's finish it off by plugging in y equals 5 and 0 in for x. And that makes 5 equal to a times 2. So a is going to be 5/2, which makes our final equation y equals 5 halves times the square root of x squared plus 4. And that right there is our final solution. Okay. Well, in the problem set today, there's some problems involving just finding a general solution. That means there's no ordered pair given. Your answer will involve the unknown constant, integration constant. And then you've got a few that ask you to solve for the specific solution. Some of those are easier than others, I'll admit. Give them all a good try. Meet up with me on the Google Meets the next couple of days, and we'll talk about some of the ones you're having problems with. But this method of separating variables is a very, very important one in this unit. You want to get a lot of good practice at it. So I encourage you to work on the problem set. Get with me with any problems you're having. And we'll look forward to hearing from you soon. We'll look back to see you guys on Friday. Thanks.